This real Unreal Engine 5.5 weapon begins at rest, kicks backward when fired, springs forward past its rest position, oscillates, and settles at 0. The runtime records a minimum offset of -180, a positive overshoot of 40, and a final offset near 0. In this lesson, we will create persistent FFloatSpringState, configure stiffness, critical damping, and mass, switch the target offset on fire and return, call FloatSpringInterp every tick, clamp motion safely, apply the offset to one pivot, and verify rest, kick, overshoot, and settled states with automation, runtime logs, and genuine Unreal frames. Ordinary interpolation can calculate the next value from current and target alone. A spring also needs momentum. FFloatSpringState stores velocity, the previous target, and whether that target is valid. The actor owns one state variable for this recoil channel and keeps it across every tick. Create a unique spring state for every independently animated value. Sharing one state between unrelated weapons or axes mixes their momentum. ResetFloatSpringState when an object is reused, teleported, or returned to a pool and the previous velocity should no longer influence motion. Stiffness controls how strongly the spring accelerates toward its target. Higher stiffness responds faster and can oscillate more visibly. Critical damping factor controls energy loss. 0 means no damping. 1 is critically damped and approaches without oscillation. This demo uses 0.35, so the weapon visibly overshoots. Mass resists acceleration and defaults to 1. These values interact. Do not tune them as isolated speed sliders. Test at real frame rates and with the same target changes used in gameplay. A camera recoil spring, weapon slide spring, suspension spring, and UI spring will need different scales and damping. At rest, target offset is 0. Fire changes the state to kicking and sets target offset to -160. After 0.15 seconds, begin return changes the target back to 0. The actor never manually adds a fixed amount to the current offset. The spring integrates the transition and momentum. Because the target returns while the rig is still moving backward, the current offset reaches the negative clamp, reverses, passes through 0, and overshoots forward. Gameplay chooses targets and timing. The spring chooses the continuous path. Every tick calls UKismetMathLibrary FloatSpringInterp. It receives current offset, target offset, the persistent state by reference, stiffness, damping, delta seconds, and mass. Target velocity amount is 0 because the target jumps and this spring should smooth that change rather than copy target velocity. The demo clamps output between -180 and +40. When the spring reaches a clamp while moving farther outward, Unreal cancels that velocity component. Clamps protect geometry, but overly tight limits can flatten the motion and hide per tuning. The current float becomes the recoil pivot's local X position. The weapon body, barrel, muzzle, and flashlight are attached to that pivot, so they move together while the stationary base and rail remain fixed. This is the same component hierarchy principle used for turret yaw. Put the moving parts under one mechanical pivot and apply only the value that pivot owns. For camera recoil, the spring may drive pitch instead. For procedural weapon animation, independent springs can drive translation and rotation, but each needs its own state. These are genuine game mode frames rendered by the included Unreal project. The cyan rest frame reports offset and velocity 0. The red kick frame shows the assembly displaced backward with an active muzzle flash. The amber return frame captures positive offset 12.2 and forward velocity over 1000. The green settled frame returns the weapon to 0. The rig, wall, rail markers, colors, flash, shadows, offset, target, velocity, and state labels all come from the same running Unreal execution. They are not generated substitutes. The Unreal automation test passed with 1 success and 0 warnings or failures. It creates a fresh spring state, simulates 9 firing frames and 240 return frames at 60 frames per second, then verifies visible negative recoil, positive overshoot, convergence near rest, configured defaults, and state labels. The runtime then proves one fire for native captures, minimum offset negative 180, maximum offset 40, final offset near 0, final velocity below the settling threshold, more than 500 spring updates, and valid true. The fixed step test catches tuning regressions. Runtime evidence catches timers, real delta seconds, hierarchy, materials, light, camera, and presentation. The reusable pattern has 4 steps. Store 1 persistent spring state per animated channel. Change the target when gameplay events occur. Step the spring every frame with delta seconds and deliberate tuning values. Apply the result to the correct component, then define a tolerance for settled. Reset state when reuse should discard momentum. Clamp only when mechanical limits require it. Test both transient extremes and eventual convergence. For recoil, suspension, camera lag, procedural animation, UI motion, and responsive props, FloatSpringInterp is an AI-friendly C++ tool with visible, testable Unreal behavior.